Okay, good morning, students. Today we will discuss the remaining part of our first unit of low power VLSI design. Here in this lecture, we will discuss about dynamic dissipation. Dissipation means dynamic power dissipation. Dynamic dissipation in CMOS, and then later on we will discuss the transistor sizing and gate oxide thickness. So let's start our topic. We already discussed in our previous lecture that basically the power dissipation is divided into two types. First one is the dynamic power dissipation and the second one is the static power dissipation. These are the two types of power dissipation. Okay, now it is represented here. Power dissipation is divided into two types. One is the dynamic power dissipation and the second one is the static power dissipation. Okay, now this dynamic power dissipation is generated. This dissipated power is generated due to two reasons. This dynamic power is generated due to two reasons. First one is due to switching of CMOS, and the second one is due to flow of short circuit current. Okay, so this dynamic power is dissipated due to two reasons. First one is the switching of CMOS and the second one is the short circuit current. Now it is clear to all of you. Now what is the mean of power dissipated due to switching of CMOS? We know that CMOS is the combination of two transistors, that is PMOS and NMOS. Okay, so PMOS is in working condition when the input voltage is greater than the threshold voltage of PMOS. Input voltage is less than the threshold voltage of PMOS. I repeat it again. When PMOS works only when the input voltage is less than the threshold voltage of PMOS. Okay, the threshold voltage of PMOS is represented as VTN. Same as the NMOS transistor works only when the input voltage is higher than VTN. Okay, it means that when the input voltage is higher than the threshold voltage of NMOS, only in the case the NMOS works. When PMOS works only when the input voltage is less than the threshold voltage of PMOS, and when NMOS works only when the input voltage is higher than the threshold voltage of PMOS. Okay, so when we provide the input voltage to the input terminal of CMOS, in that case the CMOS switch from one state to another state. Okay, it means that at one time the PMOS works and in another time NMOS works. So when PMOS works, when the PMOS is in working condition, so PMOS charge the capacitance that is connected in the load side of the transistor. Okay, and when NMOS works, in that case the capacitance that is connected in the load side will dissipate its voltage through the NMOS, because when NMOS works, so it act as a short circuit path. So when capacitor get a short circuit path, so it dissipate the voltage through this short circuit path. Okay, so because of this switching, the capacitance will charge and discharge continuously. Because of this switching, the capacitance will charge and discharge continuously. So when capacitance is charged and discharged continuously, so because of this charging and discharging, some power will dissipate it, and this power is known as dynamic power. Okay, in the second case, short circuit current. When short circuit current is generated, I already discussed here that when the input voltage is less than VTP, so PMOS works, and when the input voltage is higher than VTN, so NMOS works. But what will happen if the input voltage lies between VTP and VTN? When the input voltage lies between VTP and VTN, in that case in that case, both PMOS and NMOS is in the working condition. So when PMOS and NMOS both is in the working condition, when PMOS and NMOS both in the working condition, so it creates a short circuit path. And because of this short circuit path, there is some path is created between VDD and ground. And because of the short circuit path, some current is flow through this path, and because of this current, this current is known as short circuit current. Because of this short circuit current, some heat is generated, some power is dissipated. This power is known as short circuit power. Okay, so this dynamic power is the combination of two power. First one is the switching power, and the second one is the short circuit power. Is it clear to all of you? Now the second term is static. This static power is generated due to the leakage current, because we know that this leakage current problem occurs in the case of semiconductor. Okay, so because of this leakage current, some power will dissipate, and this and this power is known as static power. Okay, so overall power P is the combination of P dynamic and P static. P dynamic is in that are divided into two types: P short circuit and P switching power. So now in the case of simulation of any circuitry in the VLSI, when we want to simulate any circuitry in the VLSI, or we can say if we want to calculate the power in the case of any VLSI circuitry, so first we have to calculate the P dynamic power, and then later on we have to calculate the static power. Okay. This dynamic power is represented mathematically as CVDD square alpha F plus PSC. This PSC is nothing but a short circuit power. I already discussed that dynamic power is the combination of switching power. So this first term represents the switching voltage, switching power. The power is generated due to power dissipated due to switching of capacitance, and the second one is the short circuit power. This short circuit power is generated because of the short circuit current. Okay, but this second term, this short circuit power is very less as compared to this first term. It means that if we take the value of this first term as 1, so the PSC, that is short circuit power, will be 1 by 10 of this first term. It means that the short circuit power is 1/10 of the switching power. So in the case of power dissipation, the majority power dissipated due to the switching of capacitance. Very less effect will get due to the short circuit current. So we have to focus only the short circuit current. So we have to focus only the switching of CMOS, or we can say the charging and discharging of capacitance, because only in that case this power will generate dissipated, and this one is the major concern when we design any VLSI circuitry. Okay, so this dynamic power is dependent on the three basic factors. This dynamic power is dependent on the three basic factors. What is first one is the known as C. Actually, this alpha and C, this both combination, alpha is known as data. Alpha is known as data. Okay, alpha is known as data activity. So the combination of this alpha and C, this alpha is known as data activity, and along with C, when we combine this data activity with C, so we will consider all capacitance that occurs in the circuitry. Okay, the alpha and C is the we can say it as effective capacitance. So this alpha and C, that is effective capacitance, plays an important role in the case of power dissipation. Okay, the second term is the VDD. VDD is nothing but a power supply that is provided in the circuitry, and the last one is the F frequency. We already know that for the working of any CMOS, first we have to provide some input signal, and when we provide some input signal, or we can say when we provide some input pulse, so if we provide input pulse, so some time constraint is there. So if we provide if we want to speed up our circuitry, so definitely at the time the time delay that is provided in the input side will be less. Okay, so if the time delay is less, so definitely the frequency will higher. Okay, so in higher application, this value of frequency, this frequency will be high. Okay, in higher frequency, in a higher or the speedy processor, this value of frequency will be high. So if if frequency is high, so the time delay will be less, and if the time delay will be less, so the frequency of any circuit will speed of any circuit will increase. Okay, so we already represented here that this second term, that is the short circuit power. This short circuit power is 1/10 of this first term. So if we combine this both terms, so we will get P dynamic equal to 1.1 into C square VDD into alpha F. Okay, so this 1.1 is nothing but a capacitance. We represent it as K. Here K is represented as a constant. Here K is represented as a constant. Okay, here K is represented as a constant, and we know that this power what is the relation between power and energy? There is some relation between power and energy. What is that? We know that power equal to energy by time. So if we represent F in terms of T, so we can represent it as Kc into V square dd into alpha divided by T. So the numerator part is known as the energy. So this numerator part is known as switching energy. Okay, now this C, what is the C? C is known as effective capacitance. Here it is alpha C, not C. Here it is alpha C. Alpha C is nothing but a effective capacitance, and this effective capacitance is the combination of all the capacitance that generated in the MOSFET. So overall 3 capacitance are generated in the MOSFET. First one is the COX, second one is the CJ, and the third one is the C inter. Okay, the first capacitance is known as oxide capacitance, the second capacitance is known as junction capacitance, and the third capacitance is known as interconnect capacitance. Okay, so overall we can say to minimize the power, there are the 3 ways. First, we can minimize the power by minimizing the capacitance value. We can the second one is we can minimize the power by minimizing the value of VDD, and later on the third one is we can minimize the power dissipation by minimizing the value of frequency. Okay, these are the 3 ways to minimize the power, to minimize the power dissipation, dynamic power dissipation in any CMOS circuitry. Okay, now the second one is the effect of VDD on speed. Okay, we know that to minimize the power dissipation, first way to minimize the value of VDD is nothing but a DC supply voltage that is provided in the CMOS circuitry. But if we reducing the value of VDD, so because of the reduction of this VDD, the speed of circuitry is also reduces. So if we minimize the value of VDD, so to compensate this speed, we can apply a second technique that is known as parallelism. So if we connect the several circuit parallelly, and if we connect several circuit parallelly and minimize the VDD, so by using this parallelism we can compensate the speed of the circuitry. We can compensate the speed of the circuitry. Okay, some simulation software can be used. Some simulation softwares are used to calculate this behavior of MOS transistor. This simulation software are known as SPICE software. Several simulation softwares are there that is used for the study of any MOSFET. Okay, so by using some spice simulation, by using some spice simulation, we found that there is we found that we found that there is some relation. We found that there is some relation between the gate delay. We found that there is some relation between the gate delay and drain saturation current, and in the case of NMOS, and the drain saturation current in the case of PMOS. This tau is nothing but a gate delay. Gate delay, that means the difference between the two pulses that is provided in the gate of any CMOS. Okay, so when we are taking this id set and as a constant, id set and as a common term, and take it before the bracket, so we will get this term here. This second term wn represent the gate oxide width in the case of NMOS, and here wp is known as width of the gate oxide in the case of PMOS. In the case of PMOS, so we can say this drain saturation current, drain saturation current in NMOS, and the drain saturation current in the case of PMOS, drain saturation current in the case of NMOS, and the drain saturation current in the case of PMOS is directly dependent. Drain saturation current in the case of NMOS and the drain saturation current in the case of PMOS is directly depends on the gate delay. Okay, so there is also some mathematical relations is given here, such as id satu, the drain saturation, zero drain saturation. It is also known as pinch off current. Some mathematical relations are given here. That represented that every component in the MOSFET is directly related with this drain saturation, and this drain saturation current is related with gate delay. Okay, so all these mathematical relations are given here. Now some graphs are represented here. The first graph represented between id set divided by w and L. Now what is L? L is nothing but a length of gate oxide, and what is W? W is nothing but a width of gate oxide. Okay, so W by L is very important parameter. By using this parameter, we can calculate the size of any transistor. All these terms are represented here. Here a graph is represented that makes that represent a relation between the VDD minus VT and the drain saturation current. It is already represented here. These all graphs are made by using some spice simulation software. Okay, now constant of VDD reduction. We know that for reducing the power, we can minimize the supply voltage VDD, but we can't minimize VDD. We can't minimize VDD independently, because there is some relation between VDD and VT. What is that? VDD should be greater than 4 of VDD. 4 times of VT, and this VT is nothing but a threshold voltage. This VT is set by using sub-threshold static current. Now the question occurs that what is the mean of sub-threshold static current? Sub-threshold static current is nothing but a current that generated when value of VGS equals to 0. when VGS value of VGS equals to 0 at 50 degrees centigrade. One graph is represented here between the gate delay TG and VT by VDD. Okay, one graph is represented here. This y-axis represent the delay and this x-axis represent the VDD upon VT. Okay, the acceptable static current is 100 microampere for low power memory to 100 milliampere to a high speed processor. This one is the acceptable range of this static current. So according to this static current, we will get the value of the threshold voltage VTS between 0.38 to 0.68. It is already represented here. By using the acceptable range of this static current, we will get the value of threshold voltage between 0.38 to 0.68. And one thing also you have to know that for reducing the threshold voltage in every 0.1 volt, the static current will increases 10 times. When we reducing the threshold voltage 0.1 volt, when we reducing the threshold voltage 0.1 volt, so for reducing of threshold voltage 0.1 volt, the static current will increases 10 times. Okay, so this thing we should always remember in the case of designing. Now the next point is transistor sizing and optimal gate oxide thickness. Next one is the transistor sizing and optimal gate oxide thickness. First, remember that transistor sizing transistor sizing means that W by L ratio. W is nothing but a width of gate oxide, and the L is the length of gate oxide. If you are considering the PMOS, so in that case the W will be WP, and when we are considering the NMOS, so in that case this W will be the WN. So by using this W by L ratio, we will calculate the size of that particular PMOS or NMOS. Okay, so here we are taking a term WN plus WP. What is the WN? WN is the gate oxide thickness of NMOS. WP is nothing but a gate oxide thickness of PMOS. So if you are adding WN and WP, so if you are adding this WN and WP, or if you are taking the ratio of WP and WN, so each and every term will relates with the gate delay, that is tau. It is represented in equation 2.12. It is also represented in equation 2.12. It is also represented in equation 2.12. Here you can say this one is the WN. Here you can say this one is the WN, this one is the WP, and when we are taking the addition or the division of W and WP, it is directly related with tau. Tau is nothing but a gate delay. It means that every oxide width, the oxide width of PMOS, or we can say the oxide width of NMOS, also the ratio between the oxide width of PMOS and oxide width the NMOS is related with the gate oxide. Is related with the gate delay. So this term is also the major concern while we are designing, when we are designing any transistor, when we want to design any circuitry. Okay, so there is some mathematical operations is given here, that if you are taking if you are differentiating, then taking this as constant, then equating, so and equate to 0. So what we will get? We will get a relation through which we can find out that if we are taking the ratio of WP by WN less than, by using this graph we can say, if you are taking the ratio of WP by WN less than 1.3, so at that time the gate delay will reducing, but after it the gate delay will suddenly increases. Okay, so gate delay will suddenly increases. Okay, so gate delay will suddenly increases. So for proper operation, all it is always required that the value of wp by wn is greater than wp by wn is always greater than 1.3, or we can say in generalized way, the value of wp by wn should be greater than 2. There is the relation between these two factors on the basis of this simulation result. We also get a mathematical expression that is represented a relation between parasitic capacitance and this oxide thickness. On the basis of this, we can say if we are reducing the value of this oxide thickness, so directly the parasitic capacitance will decreases. And if this parasitic capacitance will decreases, so we know that the parasitic there is some relation between parasitic capacitance and the gate delay. So if we are reducing the w plus wn plus wp, so and if the parasitic capacitance will decreases, so definitely the gate delay will decrease. Okay, so this one is all about the transistor sizing, optimal gate oxide, and the power dissipation of CMOS, along with the constraint of VDD on speed and constraint of VT on speed. All these points are covered in this lecture. So on the basis of these results, on the basis of these mathematical result, we can form the graph between the gate delay and the addition between the oxide of PMOS and the oxide of NMOS. Also the second one is known as the relation between the gate delay with the TOX. Okay, so this topic is covered. I think this whole topic is covered. In next lecture we will discuss the impact of technology scaling. Okay, thank you so much.